Okay, so today we're going to get a handle on heat. I mean, how do we actually measure the energy that's gushing out of chemical reactions? The ones that happen all around us, and sometimes even right in the palm of our hand. So let's just dive right in.
It really all starts with a super simple question. Have you ever wondered about this? You crack open a hand warmer on a freezing day and boom, it gets hot. Or you twist one of those instant ice packs and it gets shockingly cold. Well, that's not magic, right? It's pure chemistry. And it's all about the flow of energy. So these two things actually have names. When a reaction gives off heat, like that hand warmer, we call it an exothermic process. The system, the chemical reaction itself, is losing energy to its surroundings, like your hands. And the opposite? That's an endothermic process. The cold pack is literally absorbing heat from its surroundings, which is why it feels so cold to the touch. Okay, so it's one thing to feel the difference between hot and cold, but how do scientists actually put a number on it? I mean, how much heat are we really talking about here? That is the big question we're going to tackle.
All right, first up, how we measure heat. Let's start with the most direct way to do this. It's all about capturing and, quantifying the heat from a reaction in a really controlled environment. The technique itself is called calorimetry, and the device we use, that's a calorimeter. And the goal is actually pretty simple. You just isolate a chemical reaction and measure the temperature change that it causes. That's it. And you know what's really cool about this? You don't need some super fancy, expensive lab equipment. A surprisingly good calorimeter can be made from just 2 foam coffee cups nested together. Seriously, they're great insulators. You just add a lid, a little stirrer, and a thermometer, and you've got everything you need to trap that heat and measure what it does. The process itself is pretty straightforward. First step, you kick off the reaction in the water inside the cups. Then, the heat is going to flow one of 2 ways, either from the reaction into the water or the other way around. Third, you very carefully measure that temperature change. And finally, you use that number to calculate the total amount of heat that was transferred. Simple. So now we've got the process down. Let's dig into the big idea, the fundamental principle that makes all of this work. And this is a huge one. It's one of the cornerstones of, well, all physics and chemistry. It all boils down to the first law of thermodynamics. You've probably heard it before. Energy can't be created or destroyed, only transferred. So in a perfectly insulated system, if one thing loses energy, something else has to gain it. Energy doesn't just, poof, disappear. And this is the key insight. This is how we actually apply that universal law. The heat from the reaction, we'll call it Q reaction, is going to be exactly equal but opposite to the heat that's absorbed or lost by the solution around it, or Q solution. See that negative sign? That's what it means. So think about it. If we can just measure the change in the water, we automatically know the change from the reaction itself. It's kind of brilliant. Okay, so let's move on to the calculation part. We've measured a temperature change, right? But how do we turn that number into a specific amount of heat, something we can measure in, say, joules? Well, to do that, we have to understand 2 things, heat capacity and specific heat. This does a really great job of breaking down the difference. So heat capacity is all about the entire object. A huge frying pan is going to take way more energy to heat up than a tiny one, right? So it has a higher heat capacity. But specific heat capacity, that's different. That's about the material itself. It's how much heat it takes to raise the temperature of just 1 gram. So since both our pans are made of iron, they have the exact same specific heat. It's an intensive property. It doesn't care about the size. And that all leads us to this, the key formula. Q equals mc delta T, or Q equals mcat, as some people remember it. So Q is the heat we're trying to find. And to get it, you just multiply the mass of your substance, that's M, by its specific heat capacity, C, and then by the change in temperature you measured, delta T. This little equation is basically the engine that drives all of calorimetry. And just look at this table. Different materials have totally different specific heats. Check out water. It's a whopping 4.184. It takes a ton of energy to heat up water compared to, say, gold, which is down at 0.129. This is exactly why water is so good at absorbing heat in a calorimeter. And honestly, on a much bigger scale, it's why our oceans are so critical for regulating the entire planet's climate. They just soak up so much heat. So we've got the direct measurement part down. But what happens when that's just not possible? Let's explore a more theoretical approach. This is where chemists get really clever and move from the lab bench over to the whiteboard. I mean,
Think about it. How would you measure the heat of a reaction that's, explosive? Or what about one that takes millions of years, like turning graphite into a diamond? You can't exactly stick a coffee cup calorimeter on that. For situations like these, we need a totally different and way more elegant tool. And that tool is called Hess's law. This is such a powerful idea. Basically, it says that the total energy change for a reaction doesn't care about the path you take to get there. We call this total energy change enthalpy. Here's a great analogy. Think about climbing a mountain. Your total change in altitude is exactly the same, whether you take a super steep direct path or a long, winding trail. That's because altitude is what we call a state function. All that matters is where you start and where you end. And enthalpy works the exact same way.
And the best part? Applying it is basically just simple algebra. If you have a bunch of reactions where you already know the energy changes, you can just treat them like math equations. You can reverse an equation, you just flip the sign of its energy change. You can multiply an equation by 2, you just double the energy. And if you add 2 equations together to get the one you're looking for, you just add their energy changes. It's kind of like solving a puzzle.
Okay, let's talk about why this all matters. We've got these really powerful tools, right? Both in the lab and on paper. But what does it all mean for us in the real world? Why is tracking this energy flow so important? Well, it turns out this stuff is literally everywhere. You know the nutritional calories you see on a food label? Yeah, those are figured out using something called a bomb calorimeter, which is basically a super heavy-duty version of our little coffee cup setup. The design of hand warmers and cold packs, it's all based on these principles. And for big industrial processes, understanding these energy changes is absolutely crucial for making things efficient and, safe. And this graph, the heating curve of water, just tells the whole story perfectly. So let's just walk through it. You see the slanted bits? That's where you're adding heat and the temperature is going up. Simple enough. But look at those flat parts, the plateaus. This is where it gets really interesting. At the first one, down at 0 degrees Celsius, all the energy you're adding is just being used to melt the ice into liquid water. The temperature doesn't budge until all the ice is gone. And the same thing happens up at the second plateau, at 100 degrees, for boiling. It's just a beautiful picture of how energy can do one of 2 jobs. It can either change the temperature, or it can change the state, but it can't do both at the same time. So here's the bottom line. From a simple foam coffee cup to the really elegant math of Hess's law, we have this incredible toolkit for tracking and predicting how energy flows. And that's really what chemistry is all about. It's a science that can measure and predict things, and that's what lets it shape our entire world. And that kind of leaves us with one last big thought. We know from the first law of thermodynamics that energy is never really lost, it's just transferred. So when we look toward the future, the real challenge isn't about creating new energy out of thin air. It's about understanding and measuring the energy we have with more and more precision, so we can figure out smarter, more sustainable ways to tap into its constant, unending flow.